Okay, we have introduced two new concepts, momentum and impulse. The reason we define momentum as mass times velocity because we realized in order to describe, we want to define something to describe how hard it is to stop an object, and then mass and velocity are the two factors you're going to consider. You're going to consider both of them. So the simplest definition is just multiply them together. And then when you are stopping something, okay, the force and the time are two factors you're going to consider as well, because they are related, right? The longer time you have to stop an object, the smaller the smaller the force you need to stop the object. So that's why we define another thing, impulse. And then, as I said, if you start with Newton's second law, you can show that the net impulse on any object is going to be equal to the change in momentum of this object. And this is called the impulse momentum theorem. So we can use, what's the use of this theorem? We can use that to estimate the average net force in a collision. That's the use of that. Because first of all, the collision in real life, they're usually very short, right? And then the force is usually very, it's not going to be constant. It's usually in a triangle. We call it impulsive force. So it rises very quickly, reaches a peak, and it also drops very quickly to zero, but the whole process it may be in milliseconds, something like that. Okay, so to measure the force in a collision is really hard. But if you rearrange this equation, we can estimate the average force in a collision by using the changing momentum, changing time, and changing momentum and changing time, they're easier to measure than a force, right? Because if you want to find the change in momentum, you just want to find the speed. And we do have very good device to measure speed and time. So that's the use of this momentum and impulse. So let's take a look at another example. In this example, I want to use this theory to explain that, okay, something everyone knows, everyone does in our life is that when you jump from a certain height to the ground, you always bend your knees. Why? Because you know that when you do that, you can avoid injuries. Okay? And why does it help avoid injury? That's what we want to figure out. So let's do this. So I want you to actually calculate the force from the ground on the person. And there's two cases with bending the knees or not bending the knees. So we're going to compare these two forces. We're going to see why bending your knees is going to help you avoid injuries. So we're going to break it into two different processes. Okay? When someone jumps from a certain height and lands on the ground, there are actually two different processes here. Right? The first process is this. It's free fall. Okay, let's assume the person jumps with a very small, almost negligible initial velocity. So the person just almost falls freely to the ground. This is the free fall, right? So free fall, we already know how to solve it. We can just use kinematics or conservation of energy. Now, the second process is the collision. There are two different processes here. Once the person lands on the ground, it's going to be a very, very short collision, right? The person is going to stop really quick, but still a collision. It's just a very short process. That's when we apply the impulse and momentum, okay, for the collision. The first process is still free fall. So free fall, I want to find the velocity, the final velocity just before this person lands on the ground. And then the person is going to carry that velocity to collide with the ground. So there are two different processes. I want to first find the final velocity of this free fall. Say if the person jumps from a 1 meter tall table. So that's going to be the height of this object. Some object starting from 1 meter from rest and then falls to the ground. I want to find a final velocity at this point. So as I said, you can either use kinematic equations or conservation of energy to find the final speed. And once you find the final speed, I want you to find the person's momentum just before his feet touch the ground. Momentum has a definition. All you need to do is just multiply. Once you have found the velocity, you just multiply that by the mass, because that's the definition of momentum. All right, so that's something I want you to first calculate. Then we're going to use that number in the second part to calculate the force from the ground on the person in this collision. All right, what is the number you got? So if you, I think most of the people that use kinematic equations, okay? Let's use conservation of energy. Don't be afraid of these new laws, new theories we learn in this class. They're actually more powerful. Not everything is kinematic equations. Let's use conservation of energy, okay? I actually like conservation of energy better than kinematic equations and Newton's laws, right? If I use conservation of energy, I would do this. Final kinetic energy minus initial plus, right? Final gravitational potential energy minus initial potential energy. And there's no elastic potential energy. I don't need to write that term at all. Equals external work. So how many forces on this guy when it's falling? Free fall, gravity. And gravity never goes to the right hand side, right? We have done that many times. So gravity never goes to the right hand side, 0. You rearrange this equation, right? Initial velocity is 0, because they start from rest. Final height, you can call the final height is 0. That's already the ground. So the initial height is just going to be 1 meter. You rearrange this equation, so this term goes away. You will get V final equals 2g times hi. Right? You rearrange this equation, 4.43 meters per second. Okay, and then 4.43. Of course, the direction is down. Right? Conservation of energy actually doesn't tell you the direction of the velocity, because everything is a scalar. It only helps you find the value of the velocity. So that's one downside of conservation of energy. But usually in a real problem, you can figure out the direction based on the information from the problem. Right? So I can just use conservation of energy to find the value. All right, so that's going to be valid. Then what is the momentum? The momentum of the person is going to be this. You multiply them together, you get 332 kilograms meters per second, and of course the direction is down. So direction is down, you can call it negative, or you just say this value and the direction is down. But anyway, so that's the momentum before the person collides with the ground. Now we're going to move on to the next part. Now I'm going to ask you to calculate the force from the ground on the person when the person doesn't bend his knees. So he's just going to keep his knees stiff. So then he's going to stop really quick. Right? He's going to stop really quick. So let's say he comes to a stop in about 2.6 milliseconds. Okay, so that's really quick. I want you to find the, estimate the average force from the ground on the person. Okay, so again, what we do is this, right? We rearrange this equation because the this is what we have, right? If you use the definition of the impulse, and then if you divide both sides by the time, you will get the average net force on the person or on this object. Okay, so all I need to do is now we're going to switch to the second process, the collision. Now the time the problem tells us, that's 2.6 milliseconds, right? So that's the delta t in the second process. You see that it's a very, very short process. Now what is the change in momentum? Change in momentum is always a final minus initial. Now what are these two final and initial values? Now in the collision, what is the final momentum? Well, final momentum is going to be mass times the final velocity. What is the final velocity of the person in this collision between the person and the ground? That's going to be 0, okay? Because the person is going to stop at the end. So the final momentum is going to be 0 for sure because the VF is 0. What is the initial momentum? That's going to be the momentum we just calculated in the first process, right? Because that's the initial momentum in the first process. In the second process, the initial momentum is just going to still be this number down, right? So if you want to still call up positive, you're going to put a negative sign here, okay? Now, let's see. Now you can rearrange this equation, put them in, and then find the average net force for me. So what is the number you got? So if you rearrange this equation, right, final momentum 0, initial momentum 0, 0, but if it's down, I still call up positive. I'm going to plug a negative number in, divided by time, so that's what I get. So you will get a positive number if you still call positive up and then you assign negative sign for this value, right? And then you see that this sign is positive. If this sign is positive and I assumed positive as the up is positive, so this equation, this number, this final answer is actually telling me the direction must be up. The average force from the ground on the person must be up, which makes sense. The person is going to be stopped by the ground. The person has a velocity down. The person is falling to the ground. How does the ground stop the person? The ground is going to have a force on the person straight up to stop this person, right? So if you want to figure that out using your own judgment. But even if you don't do that, you do the math. The math is going to tell you everything, magnitude, direction. The direction is in the sign, right? Because I already said that I'm going to assume up is positive. I stick to my positive direction. So I have to assign negative sign for this momentum when I plug it into this equation. Final is 0, initial is negative, you subtract them, you get a positive number. That's the math. That's the math. I'm not going to overthink why it becomes a positive. That's a math. And then I get the positive number for the force. Okay, so that means it's in the positive direction. What was the positive direction I picked? Up. So the answer will tell me the magnitude and the direction. Okay, I don't even need to figure it out using my own judgment. Right? So that's the force. But is this the real force from the ground on the person? Think about it. Okay? If you use this theorem, everything you calculate is a net force. You only get the average net force. You should be careful. That's a mistake people make, right? It's like when you use Newton's second law. A lot of people remember, oh, F equals ma. So if the problem says find a force on this object, they're just going to do mass times a. Oh, mass times a is going to be the force. But there may be many forces on this object, right? If you just do m times a, you only get the net force. But is this net force the force you want to find in the problem? You should read the question really carefully. In this problem, if you do everything until this point, you only found the average force, average net force on this person. How many forces on this person when the person is colliding with the ground? How many forces on this person in total? How many forces do you need to draw on this person? If I ask you to draw a Fibonacci diagram of this person. 2. Gravity is force of gravity from the earth on the person. And now I'm colliding with the ground. The ground has a force up to stop me, right? So that's another force. That's the force of the ground. Look at these two forces. If I want you to use these two forces to find the net force, what do? You tell me, how do I use these two forces to find the net force on this person? Well, you would say, well, the net force on this person must be the force from the ground, whatever this number is, minus mg. If these two forces are on this person, right? But what you just found is the net force, average net force. Did you find the average ground force? No. Did you find gravity? No. You only found this number, okay? But the problem says, I want you to find this number. What do? I'm going to rearrange this equation, right? If you want me to find the ground force, I'm going to do the force from the ground. It's going to be the net force plus mg. That's the math. That's the math, right? If you tell me these two numbers, I rearrange this equation, I will find a third number. So the problem says I want you to find this force. So there's one more step actually you should finish after this. You should do net force plus gravity is going to be equal to the force from the ground. Because of this free body diagram. I'm not making things up because of this free body diagram, right? Take a look at this, right? If there's a force 10 newtons right on this object, another force 7 newtons on this object, friction force. What is the net force on this guy? You would say 3 newtons to the right. Right? If you only find the 3 Newton force, I want you to find this force on it, you would add 3 to 7. That's going to give you the 10 Newton force. Right? So if you only find the net force using a theory, you should be careful. Is the problem asking me to find a net force, or is the force from the problem equals the net force? In this problem, no. Right? If there's only one force on this object, then the net force will be that force, right? Because there's only one force on it. Nothing's going to cancel that. There are two forces on it. You're looking for this one of those forces. You're not looking for the net force. So you have to finish this step. But in this question, it doesn't really matter, because even if you do this, right? So in this question, if I want to use that, the force from the ground is going to be equal to the net force plus the mg. You should do this. Otherwise, you're just getting the net force. You're not solving this problem. You're solving for a net force. You will do this number plus mg. Right? What is the mass of this person? 75 kilograms. What is little g? 9.8. You add them together, you will still almost get 1.28 times 10 to the fifth. Why? Because this number is going to be too small compared to this. Right? This number, what is this number you're going to get? Well, say this is 10. You get 750 almost. You add 750 to this number. It's not going to really make any difference. Okay? That's why. But you should do this step in order to find the force from the ground. And that's going to make a difference in the next part. So now let's take a look at the next part. The next part is this. Now the person is going to bend his knees. When you bend your knees, of course you're going to stop at the end. But the process is going to be much longer than you don't bend your knees, right? So if you bend your knees, you're going to come to a stop, okay, in about, say, 0.13 seconds. So in 0.13 seconds, so I'm going to ask you to do the same process, right? The only difference is that when you bend your knees, you're going to extend the time of collision. And then I want you to calculate the ground force again. So you will still do this using the final momentum 0. Does this initial momentum change? No, that's still the momentum the person carries when the person collides with the ground. That doesn't change. So the only thing that changes is actually the time. When you bend your knees, you are extending the time of a collision. All right, and then you're going to do this step. If you don't do this step, you're going to get the wrong answer, because in this case, these two numbers are comparable. Okay, now you can pause the video, finish the algebra. If you do this, what do you get? Okay, you will get, for this process, you will get 2,554 newtons. Again, you only get the net force. Is this the force the problem asks me to find? I'm not sure. I have to draw this free body diagram. Once I draw this free body diagram, I realize net force equals this minus this. But I'm trying to find this guy. I rearrange this equation, I will get this. So now if you don't add the gravity, you are going to make a mistake, because now the gravity is comparable to this. If you add them, what do you get? You get 3,289 newtons and up, because this is positive. So that's the right answer. That's the force from the ground on the person, because gravity is on it. It still needs to cancel some gravity and then provide you a net force. Now you can see that compare this force. Why do we want to do this? This is the force, the ground on your feet when you bend your knees. This is the force from the ground on you, on your feet when you don't. Compare them. Do you want that force on your feet or this force on your feet? Of course I want this. If I don't have any choice, I only have these two options. This one's better, because this one is much smaller than that. It's still a few thousand newtons, okay? You're not going to do that like, 10 times a day. But if I have these two options, I would pick this, okay? Because I don't want to get any injuries. So that's why we always bend our knees when we jump from a certain height. And we know that, even though we don't know it's a law, it's a theory, but it's true. It's always true, right? It's some life-holding truth, I believe. So I always do that. So in physics, we call it a law. One can also find the mathematical form of that law. This is the impulse theorem, momentum theorem, right? And this is always true every time. And then the ground, you don't need to when you do this, do you need to tell the ground that, hey, I'm bending my knees, you better reduce the force on my feet, because you need to obey this law? No, you don't need to tell that. Tell the ground to do that, right? It's automatic, spontaneous, because everything is going to obey this law. That's why we call them laws of nature, right? Nothing is going to break them. Nothing is going to break them. So you're never going to get a larger force from the ground if you jump from a certain height and then you bend your knees. You know that, right? You know that you are using these laws in your life. You don't call them laws. You don't call them laws. You know that's some truth, universal truth, and then you believe in, and we call them laws in physics. All right? So physics is everywhere. We use physics every day. It's just a lot of people don't realize that they are using these laws. All right, so take a look at the next slide. So all kinds of cushioning is the same idea. By extending the time of contact, it can reduce the force, okay, from the object on yourself, on the person. So that's going to help you reduce, to avoid injuries. All right, like the airbag, the landing mat, okay. All right, so that's the application of this law. Now we're going to move on to the next PowerPoint 13. Now we're going to talk about when we have a lot of objects colliding with each other. Momentum is much more useful than energy, because we already learned that, okay, if there's no constant acceleration, I can't apply Newton's second law. It's going to be hard to apply Newton's second law and kinematic equation. But we already learned conservation of energy, right? So why do we still need momentum? I can just use a conservation of energy even if I have a system and then there are many objects. We're going to see that in collisions, applying conservation of energy is going to be very hard. You can still apply conservation of energy, but it's going to be very hard. But applying momentum and impulse, that's going to be very easy. So we're going to see that. So first of all, we're going to apply this theory, impulse momentum theorem, in a system which has many objects, say, colliding with each other. And then if you apply this theory for every object, okay, there are like a lot of objects in this system and they're colliding with each other. So you apply this theory for every object, what do you get? You will get this equals change in momentum 1 for the first object. And then you apply this for the second one. This is totally math. I don't care the detail. This is always going to be true, right? Now I'm going to do the same thing for the third one. All right? Now you can do that for all the objects. Now what I'm going to do is that I'm going to add all these equations together. If you add all these equations together, the right-hand side is easy. You just get delta P1 plus delta P2 plus delta P3, ... That's just going to be the change in momentum of the system. right? That's the change of the, you have a system, you have a lot of things, and everything, the momentum is changing. You add all these changes together, you just get the change in momentum for the whole system. Now the left-hand side, what do you get? The left-hand side, you're going to get the sum of all these net impulses, right, for every object. And if you add them together, the impulses between them, like object 1 may have a force on object 2, but at the same time, object 2 has a force opposite equal on object 1. So if you add these two impulses together, you get two numbers in the opposite direction. But impulses are vectors. You add two numbers in the opposite direction, they cancel out. So all the impulses between these objects, like 1 has a force on 2, 2 has a force on 1, equal and opposite. 2 has a force on 3, 3 has a force on 2, equal and opposite. So all these impulses between them, among all these objects inside the system, they're going to cancel out exactly. So if you add in these impulses together, you only get the impulse from the outside. So you will still get an external impulse, right? Does this remind you of an equation we already learned? This looks very similar to conservation of energy, right? Changing the total energy of a system equals the work from the outside, external work. Okay, so that's the law we call conservation of linear momentum. So usually we switch these two sides. So it looks the same as the conservation of energy. So for conservation laws, we usually write the change in something of the system equals another thing from the outside. So these two laws, they're two theories, they're the same one, right? I wouldn't call them the different laws, okay? But we do have different names for them. We call this like impulse momentum theorem, but this conservation momentum. But they're actually the same law, okay? You just use this for one object, and this is for many, many objects colliding in a system. And of course, if the impulse from the outside is 0, then the total momentum of the system is going to be conserved. It's going to remain constant. Okay? So this is very, very similar to conservation of energy. So conservation laws, they're very fundamental laws in this universe we discovered. Then how do we use this theory? We're going to see that this theory is much more useful than conservation of energy in a collision. Okay, we're going to see an example. How do I use this equation? How do I use this law in a real collision? Again, you're going to just set up each side. Setting up the left-hand side is always easy. This is pretty much like conservation of energy, right? You just calculate the change of momentum for every object. The nice thing is this. You calculate change in momentum, you just do m times v for each object. So if I want to calculate the change in momentum for 1, I'm just going to be doing m1 v1f minus m1 v2 v1i. And then I do this for the second object, m2 v2f minus m2 v2i, etc. The nice thing is this. We don't have different forms of momentum defined. Right? Energy, we do have different forms, and we only studied 3 forms, the simplest 3. Kinetic energy, gravitational potential, elastic potential energy. Momentum only has 1 form. If I want to calculate momentum of anything, I just do this. That's it. Right? So for every object, I will only get 2 terms. I'm not going to get kinetic momentum, gravitational momentum, elastic potential momentum. No, we don't have such things. We just have momentum. So if you want to calculate change in momentum for an object, 2 terms, that's it. But you may have different objects in a system, so just repeat this, okay? So calculate change in momentum is actually, you're going to get less terms than energy. But you should be careful. Momentum is a vector, right? When you work with vectors, you should be extremely careful because they have directions. So when you calculate the velocity, when you use the numbers of velocity, you have to pick a positive direction. Any velocity momentum in that direction you call positive. Any velocity momentum in the opposite direction you call negative. So that you will get all the signs right. You will get the right answer. All right? So you have less terms, but you have directions on the left-hand side. So you should be careful. Now the impulse. Impulse, you just calculate use the definition to just do force times time for every force from the outside, right? Again, you don't include impulse from forces between the objects. So you may have these forces colliding with each other in your system, but you don't consider these forces because their impulses are going to cancel out. You only consider the impulse from the outside, from the environment, okay? So that's, again, pretty much like the work we calculate. The only difference is that you don't have any special forces you include in your system, right? Any force from the outside, you're going to calculate the impulse. All right? So in this class, we're not going to really worry about the right-hand side, okay? We're going to use this impulsive approximation because in real life, even if you want to calculate the impulse in a collision, it's usually going to be a very small number. Why? First of all, you only need the external force. So the external force, usually it's going to be smaller, much smaller than the forces between these two colliding objects. Think about the collision between the baseball and the stick. When the player is hitting this baseball, the force between the stick and the baseball is going to be much larger than the gravity of the baseball. So if I want to use conservation of energy, I want to calculate the impulse from gravity, that's going to be a very small number compared to the forces between them, right? So usually the forces from outside is going to be much smaller than the forces between these two colliding objects. Secondly, even if you want to consider that small force, you're going to multiply by the time. And remember, in most of the collisions, the time is going to be really short, milliseconds. And milliseconds, that's going to be 0.00, like 5 seconds you plug in. You're going to have a very small number. You're going to multiply it by a small force. At the end, you will get a very small number on the right-hand side, right? So that's why in this class, let's just forget about the right-hand side. Okay, we're just going to say, oh, the right-hand side, the impulse from the outside is going to be always small, almost zero. So we don't really need to worry about the right-hand side. So conservation of momentum, even though it's new to you, it's less familiar to you than conservation of energy, actually it's only because of the name. It's actually easier to apply because you only need to worry about the left-hand side in this class. In this class, right-hand side, we don't need to worry about that. Okay? Now, let's take a look at a real example so we see how to apply conservation momentum in a real example. Take a look at the example in slide 4. 4,500 kilogram freight car moving at 12 meters per second crashes into a 12,000 kilogram freight car at rest. The couple upon collision move together after the collision. What is the speed after the collision? So I want to find the final speed of these two guys after the collision. That's what I'm looking for. So when I see collision, I'm going to use conservation momentum, right? That's why I studied this. So there are two cars. Okay, I'm just going to call them M1 and M2. M1 moves in this direction with the initial speed 12 meters per second. M2 not moving. After the collision, they're going to move together. The collision happens really quick, right? This collision can happen in milliseconds. But after the collision, they were going to move together. That's another process. In that process, you can still do Newton's laws, kinematic equations, conservation of energy. Now I'm just interested in the collision. I want to find their final speed right after the collision. So they're going to keep moving with that speed. Okay, what happens after that, I can use a different law to find that. But this collision, I will use conservation of energy to figure that out. So in this case, I'm going to use this law. So I would have delta P1, right, plus delta P2 equals 0. Remember, in this class, when we apply conservation of energy, we don't worry about the right-hand side because it's usually very small. And then how do I find this left-hand side? Well, use the definition, right? And everything is in one dimension, so I don't need to worry about the y and x components. So it's going to be m1 v1f minus m1 v1i. That's the changing momentum of the first object. m2 v2f minus m2 v2i equals 0. That's it. Now plug numbers in. I know m1, I know m2, right? The problem says m1 4,500 kilograms, m2 12,000 kilograms. This is v1i. What is v2i? That's going to be 0, right? Because the second car initially it's a rest. Now I have all the numbers I need, right? You would say, well, v1f and v2f, I have two unknowns, but after the collision, this is a very special collision. Okay, not every collision is like that. So after the collision, they will move together. So I would call the final speed the same final, right? So now you will only have one unknown here. You can even add these two terms together, factor out VF. You rearrange this equation, you will find the final speed of this collision. All right, now you can pause the video and then find the final speed of the collision. If you rearrange this, what do you get? You can combine these two terms with final speed, right? You will get this. You move this m1 v1i and m2 v2i to the right. And then you can divide both sides by m1 plus m2. So you will get vf. Okay, what is vf? And then this is v1i. And v2i is 0. You can put the numbers in. The VF I got is 3.27 meters per second. So again, as I said, this is the speed they have right after the collision, really quick. After the collision, they're gonna still move. They may stop at the end because of friction, right? But that's something I can figure out using Newton's laws or conservation of energy, because that's much simpler than the collision. The collision is complicated, right? After the collision, if you are still interested in how they're gonna move, like the time, distance, velocity, whatever you like, you can use a different theory. But the collision, the best theory is gonna be conservation of momentum. Now we're gonna compare that with energy. So now I want you to do this. Take a look at the next part. What is their total kinetic energy before the collision? How do I calculate the total kinetic energy before the collision? Well, I'm just going to use the definition of kinetic energy, right? I don't even need to use a law. Kinetic energy has this definition, 1/2 mv squared. The total kinetic energy initial before the break, before the collision, is just going to be K1i plus K2i, right? I don't even need to use a law. I'm just going to use a definition. So that's just going to be 1/2. And I want you to do this because I want you to compare momentum with energy. Okay, we already have all these two numbers, right? The initial velocity, actually you only need to calculate one term because this term, the V2i is 0. All right, so pause the video, find the number. What is the number you got? The number I got is this. It's a very large number, 3.24 times 10 to the 5th joules. All right, so that's the initial energy of the system before the collision. Next part, I want you to calculate the total kinetic energy of these two cars after the collision. So that's called the final. I'm just going to do the same thing after the collision, K1 final plus K2 final, and then 1/2 m1 v1 final squared plus 1/2 m2 v2f squared. Now, what are v1f and v2f? Well, they have the same final velocity. So you're going to plug both of them in and find the final kinetic energy, right? What is the number you got? I can even combine them, put them together, and factor out this vf squared. All right, what is the number you got? You plug numbers in, you will get 8.82 times 10 to the 4th joules. Okay, what are we doing here? Now I want to ask you this question. Take a look at the question on slide 7. Do you think these two numbers, compare these two numbers, do you think that violates conservation of energy? Because this is the total kinetic energy before the collision. This is the total kinetic energy after the collision. Apparently, this guy is smaller than that. It's smaller than that. And if you calculate, this is only 27% of that. Okay? So this is less than 30% of that. Does this violate conservation of energy? Because I don't get two numbers the same. The kinetic energy, I just calculate the kinetic energy before, and that's the total kinetic energy before and after the collision. But I don't get the same number. Does this violate conservation of energy? What is your answer? Think about it. Do these two numbers violate conservation of energy? The answer is no. Why? Because we only calculate kinetic energy. We didn't calculate other forms of energy. There are a lot of forms of energy. Yes, there's a lot of kinetic energy has been lost in this collision. And you can calculate more than 70% of the kinetic energy has been lost. But they didn't disappear. The energy didn't disappear. It just transferred to another form. Right? And in a collision, there's a lot of going on here, right? There's a lot going on here. There's heat, there's a sound, there's also some damage. So in this case, there are many, many forms of energy involved. You only calculate kinetic energy. You can't just compare these two numbers and say, hey, they don't agree with conservation of energy. We never learned conservation of kinetic energy. We only learn conservation of energy. You have to calculate all other forms of energy. Then you can say that. So we do have very good equations for kinetic energy, very nice equation. But for other forms of energy, we don't have that very good equations. We have some approximate equations. So if you want to use conservation of energy in a collision, it's going to be hard. It's not impossible, and the energy is still conserved, so don't get me wrong. We don't use conservative energy in a collision because the energy is not conserved. Energy is still conserved. Energy is conserved everywhere in this universe. That's why it's a fundamental law. We haven't found any evidence against conservation of energy and conservation of momentum. So we believe there are fundamental laws in this universe. So energy is still conserved in this whole process, but it's just because if you want to make predictions using this conservation of energy, it's hard because you need to take into account all different forms of energy. And those forms of energy are very hard to calculate. But if you use conservation momentum, there's only one form of conservation momentum. We don't have different forms of momentum. Momentum is always m times v. Always m times v. And it's another thing that's conserved in the universe. Okay, it's very interesting. Okay, why is momentum and energy are conserved, but other things are not conserved? There are only very few quantities in this universe are conserved. Not everything is conserved. But momentum is another thing that's conserved in this universe. So if you use momentum, you set up conservation momentum, doesn't matter how many other types of energy involved, because momentum is different than energy. We don't have thermal momentum. We don't have potential momentum. We don't have that. We just have momentum. That's it. So you just need to set up m times v for each object. You do final minus initial. You can always get the answer you need. So it's much, much easier, much, much useful, much, much easier, much, much more useful than conservation of energy. So that's another reason we introduced momentum and impulse. Because in collisions, they're very complicated, but they're also very common in real life. Using conservation momentum is much, much easier than using conservation of energy. Okay? I'm going to stop here for this video.